Hey everyone, today I'm going to give a brief explanation on why Taylor series are used to discretize partial differential equations, and I'm going to give a tutorial on the method of how you go about discretizing partial differential equations, specifically in the context of flow fields. Alright, so given some kind of flow field, in order to discretize a partial differential equation, you first need to separate that flow field into individual coordinates. As described over here, this coordinate can be described as I minus 1j, this coordinate can be described as I comma j, and this coordinate can be described as I plus 1 comma j. As the flow field is a function of I and j, each of these numbers have different values at different points within the flow field. Okay, so you have different values for your flow property, or for the property of your flow at different points, and in order to discretize this partial differential equation, you have to write a Taylor series in terms of partial differential equations that represents the change in the flow property as you move a certain distance up the flow field, right? We'll get into why exactly we need to use a Taylor series to represent this in a bit, but for this example right here, u of I comma j, or u of I plus 1 comma j, this flow number right here, u2, is equal to the flow property at u1, I comma j, plus the partial differential of u with respect to the change in the x direction, multiplied by that change in the x direction, plus the second order term, multiplied by the change in the x direction squared over 2, plus the third order term multiplied by the change in x cubed over 6, right? Now, why is the Taylor series like this, and why does it correctly describe the flow property at this next point? What we can do is we can look towards an equivalent ordinary differential equation in one dimension, right? Say you have a function y equals mx plus b, which describes a slope, a linear slope, right? And then say you have some arbitrary function that is definitely nonlinear and cannot be characterized or described by simply, a linear polynomial. You need some sort of expression with multiple different polynomials in order to describe the curve of this function. What these higher order polynomials do is they allow you to describe the properties of a function at a higher degree and a higher level than a lower order might allow you to, right? So for single order polynomials, it'll only let you describe in the linear direction. For second order polynomials, you're able to describe the quadratic. For third order polynomials, you're able to describe the cubic, and so on and so forth. To convert this to a more intuitive idea, let's look at your change in distance with respect to time, and let's look at one of our analytical solutions for that. A simplified analytical solution for your change in x as a function of time is 1/2 your acceleration times time squared plus your velocity times time. Now, where does this analytical expression come from? It comes from a simplified version of the Taylor expression that describes your change in position with respect to time, right? Going back to our earlier PDE flow field variant of that, now that we've simplified it to one dimension, we can see that your x at some time t equals t plus 1, sorry about that, is equal to your x at t equals t plus 1 is equal to your x at t plus your slope dx dt times change in t plus your d squared x dt squared times change in t squared over t, aka your acceleration times change in t squared over t, your velocity times change in t, which is very familiar to this analytical closed solution over here, where acceleration corresponds to this, and velocity corresponds to that. And then these higher orders represent jerk, snap, crackle, pop, and etc. So now that we have a physical description of why these higher order terms are necessary, let's break down every element in this full equation right here. Going into the next section, we want to fully analyze the Taylor series expansion, which represents the next point in the flow field's property, right? U of I plus 1 common j is equal to U of I plus 1 plus the first order PDE times change in x plus the second order PDE times change in x squared over 2, third order plus the third order times change in x cubed over 6, etc., in the one-dimensional distance time equivalent. It's equal to your distance at x equals t plus, or x equals t plus 1 is equal to your distance at x equals t plus the velocity times your change in time plus acceleration times change in time squared over 2 plus jerk times change in time cubed over 6, and etc. And there's 3 different components to consider for this Taylor series expansion. That corresponds to both 1D and 2D, right? For point A, it's the initial value of your property at the point which you are calculating from, right? Because this right here is our change in x. We're trying to find the value at u2 using the information we know at u1 and using what we know about change in x and the different partial differential equation values, right? So we're intending to rewrite this expression and to find what exactly this is, but I'll get to that later. So ultimately that's the same for first order and second order, and A represents the value at the initial point, because this is inherently a expression that describes the change in value. Now, B and C kind of relate to each other. As I said before, when you have a function y equals mx plus b, and you attempt to characterize some other function, the red here, using a linear order polynomial, sometimes there are higher order, let's say there are higher order increases or decreases or applications to that function which can't be characterized by a single first order polynomial. That's why you have your second order, your third order, your fourth order polynomials, and each of these functions pretty much represent a different response that the function has with respect to the step input being changed. To rephrase that in better words, let's think about our 1D example, distance and time, right? You have a ball being thrown at a constant velocity, and after a constant change in t, at that constant velocity, or after a certain change of t and after that constant velocity, your distance will change in a linear x, right? Your ball will move a linear x, and that x is described by your velocity times your time. Now, one thing that doesn't consider is acceleration, doesn't consider jerk. If you intend to add these functions to the equation, higher order functions, you can't use a single order polynomial to describe the impact acceleration has over that change in t anymore. You need a second order polynomial, you need a quadratic. And that's what these C functions essentially do. They give you a higher order polynomial to characterize those higher order changes that can't be described by this change right here, right? That can't be described by this linear value. It's just a mathematical issue with first order polynomials, right? You can't describe these higher order increases, so you need a different polynomial to describe those higher order increases. You can't describe how x changes with change in t squared, so you need to have a function of change in t squared to describe how x changes with change of t squared. And that is true for every polynomial going forward, all the way to change in t to the n, right? Each of those individual higher orders need to be uniquely described and expressed by a polynomial of the same order. That's what C does, essentially. And what B does is B characterizes that polynomial function to fit our specific field/expression, right? Adds character. So while this this describes the general shape of, okay, it has a second order term. Okay, it has a third order term. The function does change with respect to t squared. It does change with respect to t cubed. This tells us how it changes with respect to t squared. How does it change with respect to t cubed? How does it change with respect to acceleration? How does it change with respect to, or yeah, with acceleration, with respect to jerk, with respect to velocity, right? Yeah, and those are the three elements of your expanded Taylor series. Next, we will write an expression, or rewrite this expression to derive for specifically our first order partial differential equation right here, du dx. Finally, we have our expression for du dx, the partial differential version, as a function of the flow property value at ui plus 1 comma j minus the flow property value at ui comma j divided by change in x. The by change of x comes from the fact that the original PDE over here is multiplied by change in x. So when we put it over to the other side, we have to divide the entire right side by change in x. And so what happens over here is then you have the second order function, or this is an expression for your du dx, but you also have to account for the higher order functions right here. The second order function, d squared u dx squared times change in x squared over 2, then you divide that by change in x, and then the same thing for the cube variant. So then this becomes just change in x, and this becomes change in x squared. And what you can describe this formula for the coefficient of the, I don't want to say coefficient, but the partial differential equation term, and if we were in the 1D example, that'd be velocity specifically. We can describe that as the forward difference minus your truncation error, where this right here is your truncation error. Going back to the analogy we had earlier, this is our linear expression, our linear approximation for this function, and then this is accounting for the terms that we didn't necessarily, this is accounting for the terms that aren't covered in our forward difference, right? And that gives us an approximation, not an approximation, the exact solution for our partial differential equation term. At higher orders, change in x squared, at smaller steps actually, we are able to neglect these higher order terms and focus on the forward difference, because as change in x approaches infinity, as change in x approaches 0, the forward difference dominates, and we can approximate du dx as a function of just the forward difference. So that's why when you have CFD software, the smaller the steps, the smaller the size, the smaller the distance between the points on your grid, the smaller your meshes, the more accurate your forward differences, or the more accurate your algebraic representation of the change in the flow field with respect to any coordinate distance is, pretty much, with smaller and smaller sizes. So this becomes just change in x. This gets really large, this gets really small. Now, for the purpose of CFD and other applications, you don't want to be using something that, something where the truncation error contains a change in x value, because a change in x value at higher order terms is, or as change of x approaches 0, is still rather large. We'd call this a first order accuracy discretized expression for the term of the PDE, and we'd want a second order or a third order accurate higher. And what that basically means is that in our truncation error, we have a term that is a function of just change in x, right? So we'd want something that is only a function of change in x squared, which I'll cover that derivation in a later video. But this is why and how Taylor series are used to discretize partial differential equations in a nutshell.